Hello dear students, welcome you all. So in this lecture, I am going to extend the discussion on the semi-empirical mass formula, right? So in the previous lecture, I have derived the semi-empirical mass formula, and that is M.A. Z, that is the mass of a nucleus that has atomic number Z and mass number A. It is equal to Z time mass of proton plus A minus Z time mass of neutron minus B, right? And V is equal to, B is the winding energy, or we can write V upon C square. This is equal to A volume energy term A minus A surface energy term into A power 2 by 3, right, minus A Coulomb energy term Z into Z minus 1 divided by A power 1 by 3, right, minus A asymmetry energy term into A minus 2Z whole square divided by A, right? Then the last term, pairing energy term, plus minus A pairing energy constant divided by A power 3 by 4. So this is the expression for the winding energy we have derived, right? Now we can put this value of the winding energy here, then I will get the expression for the total mass of the atomic nucleus, right? So I can write it M A Z is equal to Z time mass of proton plus A minus Z mass of neutron minus 1 upon C square into A volume energy term into A minus A surface energy A power 2 by 3 minus A Coulomb energy Z into Z minus 1 divided by A power 1 by 3 minus A asymmetry energy A minus 2Z whole square divided by A plus minus A pairing energy divided by A power 3 by 4. So now this becomes the expression for the total mass of the atomic nucleus in terms of its winding energy. Now here in this lecture, I am going to have a discussion on this expression. This expression is called semi-empirical mass formula, right? I have explained it all the terms in details in the previous lecture. Now in this lecture, I am particularly interested in the term that is the binding energy term, right? That we have derived or calculated in the previous lecture by taking the contribution of 5 different terms: volume energy term, surface energy term, Coulomb energy term, asymmetry energy term, and pairing energy term. If we look at all these terms, then except volume energy term, all other terms reduce the stability of the atomic nucleus, except pairing energy term. It can increase the stability if it is positive, and it is positive for even nuclei. It can be 0, it can be negative. But the other 3 terms, this one, and this one, they are negative. They are reducing the stability, they are decreasing the winding energy. Now recall the graph of unit number 1, where we have drawn a graph between the winding energy and mass number. We call that as a binding energy per nucleon graph, right? That graph was let's take it. I'm just drawing it for remembering that graph. This graph was of this type, right? This is the winding energy per nucleon, and this is the mass number, right? So how here in this actually semi-empirical mass formula, we have calculated this binding energy. This is the expression. Now I want to check whether this graph is exactly similar to the graph that is obtained from here or not, right? So I was saying that this is the graph that we have discussed in unit number 1, that is the binding energy per nucleon graph, right? We have a thorough discussion on this graph. So actually I want to check that if I plot this binding energy with mass number A, but first dividing this binding number by A, then whether I will get the graph of this nature or this kind, or it will be different. Actually it should be exactly same, because that graph was experimentally observed fact. So here we have derived this formula by using some experimental results as well as from theoretical predictions. So if this formula is correct, then the graph that we should get from here, that should be exactly this one, right? So first of all, the first thing is to divide this binding energy by A, right? Then plot it with the A. So first of all, I am going to divide it with the A. That will give me binding energy per nucleon. So I will have now, I am going to divide all these terms by A. So I will get A, B minus A, S. When I will divide this A power 2 by 3 by A, right? A will go there, it will become minus, right? So I will get after that division, I will get, you can write here, into minus 1. So I will get A power minus 1 by 3. A power minus 1 by 3. Right? Then in the next term, minus A Coulomb Z into Z minus 1 divided by A power 1 by 3 into A. Into A means 1 plus 1 by 3, 4 by 3. It will become 4 by 3, right? Now I am going to the next term, minus A asymmetry into A minus 2Z whole term square divided by A into A. A into A, it will give me A square, plus minus A pairing energy divided by A power 3 by 4 into A. So into A means 1. So 4 plus 3, 7. 7 by 3. It will become 7 by 3. Right. So these are the different terms that I got when I divided all these terms by A. This is now the winding energy per nucleon that I was talking about here. Now I want to plot this entire expression with the A, that is this one, right? But first of all, I want to plot all the energy terms, that is the volume energy term, that is the surface energy term, that is the Coulomb energy term, right? That is the asymmetry energy term, and that is the pairing. We are going to ignore the pairing energy term because we know it can be positive, it can be negative, and it can be even 0. So we can't get an exact graph. We actually have to have two different graphs, positive, negative, and 0 means no graph is there, and it will depend upon whether the nucleus is even or even odd or odd, right? So we are going to have these 1, 2, 3, 4 different graphs for winding energy per nucleon. So you can see here. Now, if I recall the graphs plotted in the books, right, I can show you some, you can see here this book, right? The graph is given here, right? Now, I don't know how this graph is plotted because in this graph, you can see here all the terms that are shown that are on the positive side, right? So I'm not able to understand how this graph is plotted. In my opinion, either this graph is wrong or it is wrongly interpreted, right? It should be explained how this graph is plotted. So actually the graph is this one. the graph that we will get. You can see here, this is the origin. This is the origin 0. This side is binding energy per nucleon, right? And this is positive side, this is negative side, and this side we have a mass number A. So you can see here B divided by N, volume energy per nucleon. You can see here volume energy per nucleon. You can see this is constant. Obviously it will be constant around this one AV, because AV does not depend upon A, and we know what is the value of AV. It is 14 mega electron volt. So it is around 14, right? You can see. Similarly, the next term is surface energy term. So surface energy term, negative AS is constant corresponding to the surface energy, 13 mega electron volt. I have put this value. Then A. So this Coulomb energy term graph that we will get, this is this one graph, Coulomb energy per nucleon. This graph, this is the graph. You can see here this one. This is the Coulomb energy graph, right? It will start from here and it will slightly increase in the negative direction as the value of A increase. You can see here, right? Actually, we have AS. I'm going to write it minus. Not this is, sorry, I call it wrongly. This is surface energy. This is Coulomb energy, but this I'm talking about the Coulomb energy. This is Coulomb energy, but the second term is surface energy. So first of all, let's talk about the surface energy. So the surface energy term is this one, red one. You can see here, this is the surface energy term. This one, and this one, right? This is the surface energy term. So surface energy term is, you can see here, minus AS divided by A power 1 by 3, right? Now AS divided by A power 1 by 3, so as the value of A increase, right? As the value of A increase, so what you will get? You will get here, first the first thing is this term is negative. So when A is 0, start from 0, then this term will become infinity. It will approach infinity. You can see here, it will approach infinity. What? As the value of A increase, it will become less negative. It will approach 0 when this A will become infinity. So you can see the same type of graph. This one, this graph, right? This graph corresponds to the surface energy term. Now I am coming to the Coulomb energy term, which I was talking about earlier wrongly. So this is the Coulomb energy term. So the Coulomb energy term, you can see here, this is the Coulomb energy term graph, right? Again, it is negative. Now you will wonder that in this case, the graph starts from here and it increases in the negative direction. Why? You look at this expression, right? In this expression, this one. In this expression, we have two factors. One is Z and other is A, right? As the value of A is increasing toward this side, right? Z is also increasing, right? And Z into Z minus 1, I can take it Z square, right? So in this expression, with the increase in A, the value of Z is also increasing. So we are taking into account the total effect of both these factors, denominator and denominator. So when Z is increasing, Z square is increasing, right? Obviously A is also increasing. So we will get a dominance of this term, square term, rather than this one, because it is 4 by 3, it will be around 1.3, A power 1.3, but here it is a Z power 2. So this power will, this factor will dominate. So we will, as the value of A increase, this term will increase, right? Or we can say this entire term will increase in the negative direction slowly. So you can see here, I explained it. This is the term that I am talking about, greenish, right? This is increasing in the negative direction. This is the Coulomb energy term, right? Now I am going to the next one, that is asymmetry energy term. So again, the same thing, asymmetry. We have A square in the denominator, right? But we have A minus 2Z whole square in the denominator. So again, what will be the effect? Effect will be the same. We have a asymmetry energy term, this one, right? So this is the asymmetry energy term, right? As the value of this both the factors are in changing with the change in the value of a, denominator have a square, but the denominator also have a square, but it is subtracted by some factors like 4z square plus 4z square minus 4az. So in total, in this particular case, the denominator factor will dominate, right? And when we increase the value of a, this entire factor starting when a is 0, right? Then what will be the result? This entire term will tends to infinity. So you can see here, this term tends to infinity. This one, this comes from a downside, right? It tends to infinity. But as the value of a increase, it is becoming less and less and less negative, and it will approach 0 when a will become infinity, right? So you can see here, this is the term. So these are the 4 different terms: volume energy term, right? The surface energy term, reddish one, right? Then Coulomb energy term, greenish, and then this is the bluish is the asymmetry energy term. So 4 energy terms are plotted here. This is a correct graph, right? I am showing you how this graph has been plotted, and this is the total winding energy that has been taken into consideration after adding up all these factors. So you can see here, now the graph is quite similar to the graph that I talk about here, right? Total winding energy, although it is starting from the negative side, but when I will add this factor, right, in this term, it will start from close to the 0 positive side, right? And I will get the same type of graph that I talk about, this type, right, that we discussed in the first lecture also. So this is very, very important graph, and the discussion that I discussed here. Actually, in many books, this graph is wrongly interpreted or wrongly plotted, right? It is very difficult to understand how these terms change. But here you can see, now I am showing you how this graph is plotted. You can see here, this one here, what I have done, you can see here, I have taken the list of all the elements right from 1 to 118 with their corresponding mass number. You can see here, these are the mass numbers. Then this is the volume energy term. I have applied the formula, right? You can see here. No, this is, yes, this is volume energy term and it is constant, right? AV 14 mega electron volt. This is the surface energy term. This is the formula. This is Coulomb energy term. This is asymmetry energy term, and this is the total winding energy. So you can see here the graph that I got from here, right? After plotting this entire data, these are the graphs that I shown you there on that pic. So this is the actual graph, right, that I got here. You can see here the volume energy term is this one, right, and Coulomb surface energy term this one, right, then Coulomb energy term this one, right, then asymmetry energy term this one, right, and the total energy, total winding energy per nucleon. Exactly the same graph that I talked about in the beginning and that we discussed in the first unit, except it is starting from the negative side. Why? Because we are ignoring one energy term, that is the pairing energy term, because it is difficult to take that into consideration in this graph because it is positive, negative, as well as 0 for different nuclei. But this entire discussion is enough to understand that how the winding energy of the different nuclei changed with the mass number, or what is the role of these different terms in this entire discussion, right? So this is all about it. So once again, I'm explaining this thing again, that the formula that we have derived for the total winding energy in different terms, right? It is very close to the experimentally observed results, right? This one, and all these terms that are plotted here, they are also in great agreement with the experimentally observed fact, right? So I am hopeful that this entire discussion is going to make you clear understanding and correct understanding of this graph. I show you, once again I am showing you that this graph as plotted in this book, you can see here, I think it is wrong, right? And in other books also this graph, I don't know how this graph is going to be interpreted as it is plotted in this book, but this is the correct way to understand it, to analyze it, and this is all about it. So thank you very much.